So yeah, a little bit of today we're going to talk about the efficient software packet processing on FPGA network cards. The paper by this group of people who did a lot of amazing work. Really big scope of the paper, spanning compilers, hardware, FPGA, and so on. So a little bit of the motivation. From our previous discussions from previous meetings on FPGA, one of the reasons why we want to put this kind of hardware in our system, in the servers, is because we want to conserve the CPU cycles, right? So there are some tasks that, are kind of boring and routine, right? So they're maybe repeated all the time and not very the task that you are concerned with in terms of your application, right? But something that has to happen. So a network stack, right? Or maybe some expensive computations in machine learning, which obviously needs to happen, but you just want them to happen as fast as possible so you can move on to the next stage and so on. So because we don't want to waste the CPU cycles on the routine and boring computations, we want to kind of offload this routine computations into the separate purpose-designed hardware, right? We build this, or we use these accelerators for different purposes. One common example was is a GPU, right? So, GPU is this specialized hardware to do some specific set of computations that happen to, be very useful in terms of rendering graphics and, doing some other highly parallelized math, right? So, that's why they became kind of useful in machine learning as well. So, the reason why we want this purpose-designed hardware is because the CPU is very general, right? So the CPUs, we can do all kinds of stuff on the CPU, but the generality actually hurts the performance sometimes. So if you have this specialized hardware, you can take a lot of optimizations, remove all the generality and build the hardware to specifically solve the problem. So we also have this kind of more general class of accelerators, FPGAs, so field programmable gate arrays. So essentially, FPGAs they actually sound too good to be true, right? Because from one point of view, we want to have this specific special purpose-built hardware to solve our specific problems, but at the same time, we kind of like the flexibility of the CPU, right? So FPGAs, they, kind of fit somewhere in the middle. So they are general enough to be programmed for different tasks or even multiple different tasks, at the same time. But they're also specific enough to allow to implement this, purpose-built hardware optimizations to solve your problem faster. Yeah, so another aspect that this particular paper talks about quite a lot, and one of the goals that they wanted to achieve is, not only use the FPGA to offload some CPU cycles, right, to offload this task from the CPU to FPGA, but also do so in a way that uses as little FPGA resources as possible, because the idea is that you can share this FPGA, the chip, you can program it for different other tasks. So, and this is kind of what the authors show in this diagram, that their FPGA, while it runs their particular application, it may have blocks that are designed for other tasks, right? So, and this is another important point of view, right? instead of building a purpose-built hardware, if you put these FPGAs into your servers, now you can have the accelerators for different tasks. So it's actually very important to try to minimize the footprint of your particular implementation on the FPGA so that you can fit more stuff into that FPGA potentially. So yeah, and this whole FPGA stuff is actually like very important. And I think the CPU manufacturers, they're betting on the FPGAs now. Back in 2015, Intel bought Altera, which was one of the largest FPGA manufacturers. And just recently in 2020, AMD, the second CPU manufacturer, the x86 CPU manufacturer at least, announced that they're going to be buying Xilinx, which is the largest FPGA manufacturer. So I think this, accelerate the FPGA to accelerate specific tasks. I think this whole notion of FPGAs are going to come closer to what we have in the CPUs, right? So, to have this ability to build the accelerators that are, general enough that can be reprogrammed, or like the functionality can be changed, things can be added, but specific enough to actually be very useful, and offload the cycles from the CPUs. This particular paper addresses the problem of packet processing. Right, so they implement something called hXDP, or Express Data Path, which is this essentially piece of software that, or the technology that allows to write programs that look at the packet before the network packet actually goes into the network stack. So as soon as it arrives at the network card, you can add the hook to inspect this packet with the hXDP. And upon this inspection, you can do several different things with this packet. You can pass the packet so that it actually goes further and goes through the network stack of your server. Or you can drop the packet, for example, so that it just doesn't exist. You can also redirect the packet. Right, so you can send it to a different machine, for example, different network card. So this kind of reminds me of the stuff that we discussed. I think it was last paper, right, about the partial failures and how they use the software-defined networking to forward stuff. So. I'm speculating, but maybe this is potentially one way to implement this layer, with the redirections on hXDP path. But totally speculating, not not an expert here. So that hXDP, as I mentioned, it hooks up to the network driver early on, before that packet has a chance to start processing and actually consume the resources of the rest of the network card, or the CPU cycles and memory and whatnot. So that hXDP runs on something called eBPF, which is Extended Berkeley Packet Filter, or something like that. So in a sense, eBPF is this, or at least in a version that is used here, right? It's the virtual machine that sits in the Linux kernel. Right, so it's a fairly small virtual machine with a fairly limited instruction set, but it sits at the kernel level, and the programmers can write this eBPF programs that essentially execute at the kernel level, but they stay within this boundary of this limited virtual machine. So has the benefit of being at the kernel, but protected by the virtual machine boundaries. And Express Data Path typically is implemented as this on top of this eBPF virtual machine. So the way things would work with the hXDP, right, is you have a packet that will come to the network card, and one of the first things that it's going to see is this XDP hook, right? So this hook is going to essentially say, oh, I have a packet, but I do have this XDP program that needs to look at that packet. So it will ship it to this program, which in normal circumstances would run this program on this eBPF virtual machine and do one of few things. Like I mentioned, it may pass the packet to the network stack. It may redirect, may drop, or maybe return the packet to the sender. So what is hXDP then? So this is the stuff that this paper actually implements. So the hXDP, okay, I wrote here replaces, but it's more like adds or augments the regular XDP implementation with the one running on FPGA. So when this program from the hook is invoked, right? It goes through this. Essentially, it has to compile, right? So this program has to compile to bytecode of this virtual machine, maybe do the just-in-time compilation or whatnot. But what they have added here is the ability to not do the regular eBPF execution that runs in this kernel inside this eBPF virtual machine, but they allow the programmers to specify that they want a particular eBPF program to run on this FPGA hardware. So, and this hXDP is the FPGA hardware implementation of the XDP, which, because it runs on this eBPF, so in a sense, this is kind of a special build hardware implementation of the eBPF virtual machine, right? So they do have a couple of components that are super crucial for the operation of this whole system, and one being the compiler, right? So they need to take this eBPF program and they need to compile it into in their custom instruction set that will run against that custom FPGA module, right? So the compiler does a lot of optimization. So this is where a lot of the things are being optimized to run efficiently on these FPGAs, versus the regular virtual machine. And these optimizations include things like removing unnecessary instructions. So the paper mentions that in the regular eBPF implementation of XDA, you would have instructions that do the boundary checks, for example, to make sure that you don't try to access the memory you're not supposed to access, and things like, things like that. So, but since you're running on this FPGA that doesn't have the outside memory, so it's like purpose-built, the only memory it has is the the program and the packet information. These boundary checks kind of become unnecessary, right? So they will just waste the CPU cycles, but they're not needed because you cannot access any like the actual system memory. You just running on this hardware box, the FPGA. So the compiler actually gets rid of a lot of this unnecessary instructions like boundary checks. It does combine some instructions together. So they have extended the eBPF instruction set to include more instructions that they have then implemented in the hardware to combine multiple steps in one step, so they can do it in one clock cycle versus multiple clock cycles. There are optimizations like zeroing the new variables so that the program doesn't spend time setting, for example, some array of some struct to like all zero values instead of just having whatever is there in memory. Load store size optimizations, like they do mention that I think by default eBPF a virtual machine only loads and stores words of like 2 bytes. So like if a lot of the information is more than 2 bytes, like pieces of the header that are 6 bytes or so. So they added the load and store instructions of different sizes, 2, 4, 6 bytes, so that they can, you know, maybe grab that piece of the header that they're interested in 1 clock cycle versus, you know, let's say 3 clock cycles. Another big aspect of you know, what they try to do is instruction level parallelism. And that is important because you know, FPGAs are kind of designed for parallel computations instead of sequential computations, and that's mostly because, you know, the clock cycle, the clock speed is rather slow. So you know, they don't have a lot of clock cycles per second. So it's beneficial if you can just implement multiple like parallel modules to run. But apparently these eBPF programs, they're not very parallel. So they try to achieve some instruction level parallelism, and you know, they use the pipelines and things like that. So pipeline parallelism as well. Yeah, and so moving on to the hardware side. So this hXDP is implemented in the hardware as one block on FPGA. They actually implemented all of the components of XDP entirely in FPGA, so that you know, once you have this packet, you can run the entire program completely in FPGA without having to go and do any work on the real CPU and you know, real memory and stuff like that. So yeah, their hardware implementation is like this 5 components, right? So programmable input queue is how the packet is being loaded. It's loaded 1 word at a time with the 32 byte words. So you know, the packet will have multiple words, but it loads 1 word at a time. The active packet selector has the buffer to fit the packet, and it, you know, keeps you know, loading this packet 1 word at a time, and essentially ships the packet to the, you know, to the actual processing core, which is this Sephiroth. So this is more like the implementation of that virtual machine, well, or extended virtual machine rather, because of their custom instruction set. So once the instruction, or once the packet is here and becomes available, it can be loaded into the processing. You know, the program is going to execute, and they do have a 4-stage pipeline here. So they fetch the instruction, they decode the instruction, execute the instruction, and then they commit the result of the instruction. So maybe like saving stuff to memory or things like that, or you know, moving on. Helper function module is a kind of interesting thing too, because in order to run that XDP, run XDP programs entirely in FPGA, they have implemented a lot of helper functions that exist in the XDP technology entirely on FPGA, right? So these helper functions apparently don't change that often. You know, they just hard-coded these helper functions in the hardware so that you don't have to get out of the FPGA execution to just run some helper function and then resume. And the memory map, that's you know, pretty much just like a memory memory map. You know, manages the memory for that virtual machine. So the program, when the program finishes executing, it will you know, return back to the packet selector, you know, into the write buffer, and eventually the modified packet will be outputted. They do implement quite a few hardware optimizations here, which obviously help them improve the performance. So early processor start is when they start start running the program, start running the actual like virtual machine before active packet selector APS has received all the frames of the packet. And their logic here is that most of the programs that they have seen, and actually all of the programs that they have run, they really start by looking at the beginning frames of the packet first anyway. So they say, we can start, processing because as soon as we have these few beginning frames, and that will not cause any pipeline stalls in most of the cases. So don't have to wait for the full packet to load. You can already start processing that packet. Program self-state reset. This is the hardware implementation of the zeroing function, right? The compiler essentially removes all the array initializations to zero because the hardware always resets the stack and the registers to zero, right? So because the hardware always does that, you don't have to waste your CPU cycles on this empty assignments, not CPU cycles, the FPGA cycles. Data hazards reduction, that's another pipeline optimization that deals with the commands that go one after another in a pipeline, but have some dependency. So if command one actually changes some memory that command two needs, that will be a problem for the command two because now essentially you have to restart the command two. So, you wasted the however many stages the command two was in. So they do implement result forwarding so that the early command can pass the result to the command in the following stage of the pipeline in case it needs that result, so that they don't have to reset the pipeline. Parallel branching. So another kind of interesting thing, our CPUs, they do have like branch predictors and complicated logic like that to try to guess which branch is going to be taken. Obviously, that's missing on the FPGA, but they do say that in some cases they can, at least in the hXDP programs, they have like a sequence of branches. So if they have sequence of branches, they can try to run these branches in parallel and just order them by the priority. The innermost branch will have the lowest priority, and the outermost, if statement have the highest priority, and by looking at this priority, they can run branches in parallel and eventually make the right decision. Early exit, that's also like saves them a few CPU FPGA cycles when the program terminates. Oh yeah, another important thing that I forgot to mention here is that they do have 4 parallel blocks of the pipeline, right? So this guy is like a 4-way parallel, and so they also have the bus that can handle 4 parallel reads and writes, and yeah, like all the interactions are like 4-way parallel, at least possible to be 4-way parallel. The implementation. So they use the net FPGA developer prototyping card that has the Xilinx FPGA clocked at 156.25 megahertz, which is a lot less than the clock of the modern CPUs, and they actually use very little resources on that FPGA, right? So they use only around 10% of the logic resources and 2% of the register resources, and very little VRAM, which is the RAM that's located inside the FPGA. So I guess, when it comes to the goal of, having the small footprint, they definitely achieved that. So yeah, when it comes to the evaluation, so this figure talks about different optimizations that they had and how much gain they, how much performance is gained with each of this optimization. So like no zeroing, pretty simple stuff, but in some applications, so this is different applications on the x-axis, right? In some applications, you can see, can give them up to 12, like 13, 15% gain, which is pretty impressive. Bound checks, right? So removing these unnecessary instructions for the memory bounds and things like that, can give them up to almost like 20% improvement in some applications. The three operands is when they, it's like their extended instruction set that allows them to combine a few instructions into one. So by doing that, they also achieve quite a lot of improvement across the board in all kinds of applications. And so is the 6-byte load store, so it gives them variable performance. I guess that depends on the type of XDP program. This evaluation is comparing the hXDP against the actual CPU, right? So in terms of the throughput, packet processing throughput. So, and they do here, figure 10, two simple applications. And you can see that the hXDP actually does a little bit worse than the CPU running at 3.7 gigahertz, but outperforms the CPU running at 2.1 gigahertz. So it's somewhere in between. And so the authors kind of claim that most of the server CPUs they tend to be on a lower frequency range, especially the high core count CPUs. So 3.7 is not very common in a server market. So they say that roughly speaking, they achieve similar performance to an x86 CPU core. This is just one core evaluation. On top of that, they say that they do have a much better latency. All right, so they can decide what to do with this packet quicker, and that's I guess another interesting advantage. Some figure 12, I believe, is some benchmarks that do similar comparison as figure 10, but more like a benchmark applications. And the results are kind of similar, right? hXDP does perform worse than 3.7 gigahertz core, but in many cases it can compete or outperform the 2.1 gigahertz core, except in like this kind of except in these few applications. Another thing that I want to mention is that the CPU that they used for the evaluation is 6.5 years old. So this is not a state-of-the-art CPU. And that will be it for my little presentation.